Imagine a universe so vast that our current understanding barely scratches its surface. What lies beyond the observable horizon? Is it an endless expanse of nothingness, or something more? Our observable universe, it's what we can see, what we've mapped out with precision. But here's the thing, that's not just because of our technology or our telescopes. The problem is, light takes time to travel, and the farther away a star or galaxy is, the longer it's been sending signals our way. That means, even if we point our most advanced instruments at the edge of the observable universe, there are regions beyond that we're seeing as they were 13 billion years ago. That number sounds absurd until you realize what it implies. Everything we've ever observed in the cosmos is a snapshot from a bygone era. And when you get to the edge of our observable limit, you start to wonder what lies beyond. Is there an unobservable universe lurking just out of sight? The cosmological constant, a value so slippery it's been called a fudge factor by some critics. That number sounds absurd until you realize what it might imply, that space itself is accelerating outward at an alarming rate. But here's the thing, this accelerating expansion has been going on for billions of years, long before our universe was even born. What does that say about the origins of the cosmos? Was there some kind of initial burst of energy that set the whole thing in motion? Or did it just start accelerating like this out of nowhere? Some scientists argue that the cosmological constant is a necessary correction to Einstein's theory of general relativity, but others see it as a bit of a cop-out, a way to make the math work without fully understanding what's going on. And what happens when we push these values further and further back in time? Do they start to make sense, or do we just get more noise? The problem of the missing mass is a bit of an understatement, really. We're talking about a discrepancy that's been nagging cosmologists for decades. The observable universe, as far as our telescopes can reach, should contain enough mass to slow down its expansion, but observations suggest otherwise. Galaxies are moving too fast. Stars are behaving erratically. It's as if there's an invisible hand pulling them along. Now, some might say this is just a minor glitch, but the numbers don't lie. The missing mass amounts to roughly 85% of all matter in the universe. That sounds absurd until you realize what that implies. Our understanding of gravity and large-scale structure is fundamentally flawed. We're not just talking about a few loose ends, we're talking about a paradigm shift. And yet we still have no idea where this dark mass resides. Is it hiding in dark matter particles? Or is there something more sinister at play? The mystery deepens. Looking at the observable universe, it's become increasingly evident that something doesn't add up. We've got our mass energy budget, the total amount of energy in the universe, and when we factor in all the things we can see, it falls short by a significant margin. That number sounds absurd until you realize that this discrepancy is actually an invitation to consider what's hidden from us. Enter dark matter and dark energy, two entities we've dubbed because we literally have no idea what they are. Dark matter makes up around 27% of the universe's mass energy budget, yet it refuses to interact with light in any way. It's as if it's been carefully edited out of our perception. And then there's dark energy, which is thought to comprise a whopping 68% of that budget, but its nature remains shrouded in mystery. What does this say about the universe we think we understand? Does this not raise more questions than answers? We'll delve into these enigmas next. The observable universe may be all we can see from our vantage point, but the truth about its size and scope is far more complex. The expansion of the universe, which started with the Big Bang, is a well-documented phenomenon. However, that expansion comes with an interesting caveat. It's not a steady, linear growth. In fact, as we look further out into space, galaxies are moving away from each other at an accelerating rate. That acceleration might seem counterintuitive after all. Shouldn't the universe slow down eventually? But the truth is, this expansion is still largely driven by dark energy, a mysterious force that's pushing matter apart with an eerie efficiency. And yet, despite our best efforts to understand it, we're still not sure what's driving this acceleration. Is it a fundamental property of space itself, or something more? The universe may be expanding, but the truth about its underlying dynamics is still shrouded in mystery. We're about to venture into the uncharted territory beyond the event horizon of our observable universe. The event horizon marks the point of no return around a black hole. Any matter or radiation that crosses it is trapped by gravity, effectively lost forever. That's a daunting thought in itself, but what lies beyond? Some theories suggest a realm where the laws of physics as we know them begin to break down, and our understanding of space and time becomes increasingly tenuous. It sounds absurd until you realize that this beyond isn't just a metaphorical state, it's a literal expanse of unexplored cosmos. What does this mean for our current grasp of the universe? We've been trying to peer into the abyss using instruments like gravitational waves and cosmic microwave background radiation as beacons. But the truth is, we're only scratching the surface of what lies beyond the veil. And that's precisely where the most fascinating questions begin. What kind of laws govern this unseen cosmos, or do they even exist? We'll explore these enigmas in the following sections. If our observable universe is just one tiny droplet in an infinite ocean, it's mind-boggling to consider the sheer scale we're talking about here. That number sounds absurd until you realize what it implies. That there could be entire universes beyond ours, each with their own laws of physics and realities. But if that's the case, why haven't we seen any signs of them? The silence is deafening, yet it also raises a fascinating question: what would happen if our universe were somehow aware of its neighbors, but they're completely inaccessible to us? Could it be that we're just a tiny experiment in this vast cosmic laboratory, and the laws of physics as we know them are nothing more than a local anomaly? The problem with asking what's beyond our observable universe isn't just a matter of distance or scale. It's about how we think about existence itself. When we talk about the accelerating expansion of the cosmos, that number sounds absurd until you realize it's not just about galaxy moving away from us, but our very notion of space and time unfolding in ways we can't quite comprehend. The implications are staggering. If the universe is expanding, does that mean there are regions beyond what we can see where the laws of physics as we know them break down? Or perhaps even cease to apply altogether? That's a daunting prospect for any cosmologist, one that challenges our understanding of existence in fundamental ways. The multiverse hypothesis, a solution or a cop-out? On one hand, it offers an elegant explanation for why our universe's fundamental constants are so finely tuned. The idea being that we're just living in one of many bubbles, each with its own unique set of laws and properties. That number sounds absurd until you realize the sheer scale involved. Countless universes beyond our own, each containing their own unique realities. But here's the thing, it also raises more questions than it answers. What drives the creation of these new universes? Is it some grand cosmic process, or simply a statistical inevitability? And just how do we even begin to test this hypothesis when we can't observe any of these other universes directly? It's as if we're trying to solve a puzzle with missing pieces, and the multiverse hypothesis is our best guess so far. But does it really explain everything? Or is it just a convenient way to sidestep the real challenges of understanding the cosmos? Inflationary cosmology. That's the current go-to explanation for what happened in the first fraction of a second after the Big Bang. It suggests our universe is just one tiny bubble in an endlessly vast multidimensional space. Sounds absurd until you realize that it neatly solves some pretty big problems in our understanding of the cosmos. For instance, why do we see the cosmic microwave background radiation so uniformly throughout the universe? That number sounds incredible, 10 to the power of 50, but what it means is that's how many times larger than ours this multidimensional space is supposed to be. Now, here's where it gets interesting. Inflationary theory relies on what's known as a slow roll parameter, which essentially determines how long our universe was in this rapid expansion phase. But the thing is, we still can't definitively measure that slow roll parameter from within our observable universe. It's like trying to gauge the curvature of a mirror when you're standing right next to it. The farther out you look, the more blurry everything becomes, and that's precisely where inflationary cosmology starts to get shrouded in mystery. Now, some might see quantum fluctuations as the ultimate cop-out, an attempt to explain the unexplainable by invoking random chance. And I'll be honest, that's not an unreasonable perspective. After all, these fluctuations are incredibly tiny and their effects are often short-lived. But what if they're more than just noise in the system? What if they're a doorway into the unknown? The idea of bubble universes proposes that our reality is just one of many, each spawned by a quantum fluctuation in a vast multidimensional space. It's a notion both exhilarating and unsettling. It suggests that everything we experience is but a fleeting moment within an eternal sea of possibilities. And yet, this idea still hangs precariously between theory and speculation, leaving us with more questions than answers. What lies beyond the edge of our observable universe? Is it a boundless expanse of new universes, or something far more sinister? The concept of cosmic cycles and eternal returns has been proposed by various theories within cosmology, including the eternal inflation and cyclic models. It's an idea that suggests our universe undergoes cycles of expansion and contraction, potentially resetting in a manner akin to a cosmic reboot. That number sounds absurd until you realize the scale we're talking about here: billions of years, or even more, spent in repetitive cycles. The implications are far-reaching. If this theory holds water, it would mean that our universe is not unique, but rather one iteration in an infinite series. And what does that do to our understanding of time itself? Is it a fixed, linear concept? Or is it cyclical, with events repeating themselves like some cosmic Groundhog Day? The anthropic principle, it's an idea that sounds almost too simplistic to explain our universe's mysteries. Yet, it's precisely its straightforwardness that makes it so unsatisfying. The basic premise is this: if we observe the universe being governed by certain laws and constants, then that must be because any other combination would make life as we know it impossible. Sounds like a cop-out to me, but hear me out. That number sounds absurd until you realize it's not just some made-up figure. It's based on observations of our cosmos' fundamental parameters. The fine-tuning argument suggests that if the cosmic microwave background radiation were even 0.1% stronger, galaxies wouldn't have formed as they did, and life would likely be extinct. What does this imply about the nature of reality? That we live in a universe tailored for human observation, or is it just an illusion born from our limited understanding? The observable universe is like a canvas stretched across the vast expanse of space-time. But what lies beyond its frayed edges? The concept of a fabric that weaves together matter and energy becomes increasingly tenuous when we venture into the unknown. Some theories propose that our universe could be just one bubble in an endless sea of multiverses, each with its own cosmic landscape. That number sounds absurd until you realize the sheer scale it implies: tens of billions, possibly even infinite universes, all floating in a multidimensional space. The mind struggles to wrap around such a notion, and yet it challenges our understanding of what we mean by reality. We're forced to confront the possibility that our universe could be just one tiny, insignificant speck within an infinitely vast multiverse. But if this is true, then what does it say about the nature of space, time, and causality? Can we really speak of a unified fabric when the very notion of beyond becomes so fluid? The concept of an unbounded universe challenges our fundamental understanding of space and time. If there's no edge, no horizon beyond which the cosmos ends, then what lies ahead? That number sounds absurd, billions of light years in every direction, until you realize that it's not about distance at all, but the limits of our perception. We've been searching for dark matter, a hypothetical substance thought to make up 27% of the universe. Yet despite decades of effort, we still have no idea what it is. The implication is clear. Perhaps the most fundamental aspects of reality remain beyond our grasp. Join me as we venture into the unknown and explore what lies beyond the observable universe. The truth may be more surprising than you think.